Okay, so we'll be talking of the consequences of special relativity today, having been introduced to this subject in a previous lecture. Okay, so we'll be talking mainly on length contraction, but of course, before that, we'll spend some time in learning how velocities are added in special relativity. Okay. As opposed to this the Galilean velocity addition formula that we are so well used to. Right. So, if you want to come to the subject, we just summarize a little bit of what we did last time. So, we were talking of Newtonian mechanics being invariant under Galilean transformations. Electrodynamics, I mean the laws of electrodynamics, especially Maxwell's equations. We saw that they were invariant under Lorentz transformations. So, it was a peculiar situation, branch of physics and another branch of physics not being invariant under the same transformation. Okay. And it's actually this reconciliation of transformations of transformation laws of mechanics and electrodynamics from a theoretical sense, which led Einstein to the special theory of relativity. Of course, having mentioned this, I mean I should also mention the Michelson-Morley experiment, because had that not been there, it would have been very difficult to see the really need for such a theory. Okay. Right. So, we recapitulate the postulates of relativity once again. The principle of relativity the states, of course, that it's a very basic principle. The laws of physics are to be same in all inertial systems. So, there is no preferred inertial system. Okay. So, what does it mean? It means that if you are in a system and you do an experiment there, and then there is another system which is moving with an uniform velocity with your system, you will not be able to differentiate that. So, basically systems which move with uniform velocity relative to each other, they are absolutely similar in the sense that the laws of physics are going to be the same in all these systems. Okay. The second postulate, and it's very important here, it's the principle of the constancy of the speed of light. Okay. Well, I mean in simpler words, it says that the speed of light in free space, it has to be it has to have the same value. I mean, I've written c here, and if you know that it's 3 into 10 to the power 8 meter per second, I mean, which is well, it's almost 3 into 10 to the power 8 meter per second. We know that it's around 2.99 something in all inertial systems. Now, this in the first instance may sound very strange, because if you think of our everyday experience, suppose you shine a light, let's say you light a torch, and then in the direction of this light, let's say you are moving in a vehicle with an imaginary vehicle, of course, in a very fast way. So, let's say you are moving with 2 into 10 to the power 8 meter per second. So, what happens? So, what speed will you see the light, see this light from your normal experience of Galilean relativity? Okay. So, Galilean velocity addition formula and all these things. So, the light is moving forward 3 into 10 to the power 8, you are moving in the same direction in 2 into 10 to the power 8. So, you are supposed to see the light in 3 minus 2, that is 1 into 10 to the power 8 meter per second. Well, relativity tells you that no, you are going to see it 3 into 10 to the power 8 meter per second, that is all. Well, we will see how this is possible, because if you believe in this Galilean transformations, if you do this thing in Galilean transformation, of course, this does not come about. So, there is another transformation where such thing is possible, and that is we saw what that was. That was actually Lorentz transformations. And if you I am just summarizing the transformations once again for you. If we have, let us say, a frame S prime which is moving with a certain velocity v, that's a certain uniform velocity I should add, with respect to another frame s. Okay. So, they have the, let us say, the common x prime x axis here, and then a point, a general point is x, y, z, and then you put in the fourth component, the time here, and then in the same point from the s prime frame, that is x prime, y prime, z prime, and t prime, and then these relations are given by the transformation equations, which you see here. So, it is x, how does the quantities in the primed frame relate to the quantities in the unprimed frame. Okay. So, that's that's given by the Lorentz transformations. So, here you see x is equal to gamma times x prime plus beta c t prime. Now, I've defined what these betas and the gammas are. So, beta is also, it's v by c. So, it's dimensionless, and gamma is 1 by root over of 1 minus beta square. Okay. If you write it in this form, you will see that when you write the time component, it has almost similar looking expression. So, of course, instead of time, I multiplied that by c, that is the velocity of light. So, that it has the dimension of length. Okay. So, I got c t. So, you see compare this the equation for x and compare this equation for c t. Okay. You see that it contains, in the equation for x you have both x prime and t prime, and then in the equation for c t you have both t prime and x prime, of course, in this opposite fashion. So, it looks very symmetric. So, it is quite useful to write it in this way. But for the sake of simplicity, and because we are doing this for the first time, I will use all these expansions whenever we come across it. Okay. So, what are the limits? I mean, does this in some limit go back to the Galilean transformation? Well, actually it does. Where does it do so? At small speeds. That is, if one is moving with speed much lesser than the speed of light here. So, you see v is much lesser than c. So, of course, v square by c square, that tends to 0 here. Now, you can immediately figure out that x prime, it becomes, you know, this the quantity below the denominator for x prime is equal to x minus v t divided by root over of 1 minus v square by c square. So, this turns out to be just the Galilean equivalent, that is x prime is equal to x minus v t, and since we are moving along the x prime direction. So, the y primes and the z primes are the same. Okay. Now, what happens for the t primes? Okay. Now, it is interesting, in Lorentz transformation, the times in both these frames are not the same. They are also dependent on the coordinates, on all the space coordinates of the system. It's evident from this equation itself. Okay. Now, at small speeds, smaller, much smaller than the speed of light, that is, you will see that these times t prime and t, they become equal, they become approximately equal. Actually, if you do this, if you take v by c to be much less than, so it is almost tending to 0, it is much less than 1, it is tending to 0, that is. Okay. So, that is the thing that we get. Lorentz transformations, they go to Galilean transformations at small speeds. So, that is the thing. So, at smaller velocities, Newtonian mechanics is still the thing that one can follow. I mean, that's it, that's what we do in our daily lives. I mean, we in our daily lives rarely do we go at speeds, such high speeds as the speed of light. Okay. So, the Newtonian mechanics is valid, is correct at small speeds. Okay, but having said that, let us now have a look at how velocities are going to be added in these two frames. Okay. So, what are the relative velocities, or what is the Galilean velocity addition formula here? Okay. I'm sorry, let's say the Lorentz velocity, the Einsteinian velocity addition formula according to Lorentz transformations, because the Galilean velocity transformations addition laws we have already done. Okay. But how do you do it? I mean, the process is similar. If you remember, I have drawn this this diagram for these frames. Once again, see x. Oh, by the way, the z axis is always there. It's protruding out of the screen. I've just not drawn it so that this picture looks a less clumsy. That's all. Okay. So how do you find the velocities in each of these frames? You're going to do. You're going to take this differential, this dx by dt. Now remember the coordinates you're going to take for each frame, and then the time which is suitable for that frame itself. Okay. Now, so in the S frame it is dx by dt, and in the primed frame it is obviously dx prime by dt prime. Remember in when we were doing this Galilean velocity addition formula, this t and t prime were the same, but here they are not. Okay, I mean, just for the for the sake of simplicity and just for your remembrance, I have listed it on the left. So you see that they are not the same. So if you take dx prime by dt, it's not the same as dx prime by dt prime. Okay, but you need to take this properly. Now, if you do this, if you do dx by dt and du prime dx prime and u prime is equal to dx prime by dt prime, we are going to land up with the velocity addition formula. And so, how does it look like? So what is the velocity in S frame, having known the velocity of a particle or some velocity in the primed frame? So that is the one given on the left hand side of your screen. You will see that if the S prime frame is moving with a certain uniform velocity v, and then in this frame a velocity is measured as u prime, this velocity in the unprimed frame is going to be measured as u prime plus v divided by 1 plus u prime v by c square. Okay. So, this is the Einsteinian velocity addition formula. Okay. Yeah, just to remind you, had this been the normal or the more familiar Galilean velocity addition, you would not have the denominator here. You just have u would be just u prime plus v, that is all. Okay. But then in some limit, as we said, I mean, these transformations go at small speeds, the Lorentz transformations become the Galilean transformations. So, too here it must be so. Here these velocity addition formulae must go to the Einsteinian formula must go to the Galilean formula at small speed. So, we will check that, we will check that. Okay. So, similarly, of course, you can do the reverse transformations and find u prime is equal to u minus v divided by 1 minus u v by c square. So, that you find, so if you know the velocity in the S frame, so how is it, so what is the velocity u prime you are going to measure in a frame S prime, that is, which is moving away with a uniform velocity v. Okay. So, as we are talking of the limits, so at small limits, when u is small, v is small, you immediately see what? You immediately see that this denominator, so u v by c square, this becomes negligibly small, it is almost equal to 0, you might say. So that u prime is equal to u minus v, or if you added, if you are fastidious about this word addition, so u is equal to u prime plus v, that is all. So, that gives us the Galilean limit, okay, at small speeds. Right. How about some examples? Let us see what happens if in with this Einsteinian velocity addition formulae, where you have a frame which is moving, let us say your S prime frame is moving away with a velocity 0.9 c, that is c being the speed of light. Okay. And in this S prime frame, you measure some speed speed of some object. You know, things can have such large speeds, such relativistic speeds. Some subatomic particles do have such large relativistic speeds, um, to be like 0.9 c, right. So, if you directly go and apply the Galilean formula, you know, it is 0.9 plus 0.9, you are going to get more than c. Of course, you know that that is forbidden relativity. So, how is it that comes, what is it that comes here? So, for u prime you are going to substitute 0.9 c, for v 0.9 c, and then in a denominator you see 1 plus 0.81 c square by c square, and then and voila, you get something like 0.999 c. Okay. So, it is still less than c, right. So, we have checked that even if individual velocities we have in this particular case is almost touching c, the added velocities from the Einsteinian formula, it still gives you less than c, I mean, as it should. Okay. Yeah, but the interesting case is, you might say, is what happens if one of the speeds is c itself. Okay. That is, if u prime is c, okay, in S prime frame, which is moving with a velocity some v with respect to the S frame. So, what is the speed that is seen in u? So, in other words, so this is a case you have, let us say, your light photon. So, you have a photon or speed or light which is moving with speed, of course, with the speed of light c in one frame. What are you going to observe in another frame, okay, with respect to which your frame is moving with a certain velocity v. Okay. So, this is a direct consequence, you are going to test that, it is a direct consequence of the second postulate of relativity. So, u prime you are going to substitute by c, v is of course the speed with which the S prime frame is moving with respect to the S frame, and then the denominator you have 1 plus c v by c square, and what does it give you? It gives you just c. Okay. So, that is the speed of light is the same in all inertial frames. I mean, this we had started with the postulates, no wonder that is so, but then at least you verified here that the Einsteinian velocity addition formula that we just use right now is consistent with these postulates. Okay. So, just one final example perhaps to find the relative velocities of particles. So, let us say you have two particles A and B which are moving in opposite directions, okay, one moving towards left with with minus c by 12. This plus and minus is just tells you the direction is different, that is all, the vector direction is different. So, they are moving with speeds half the speed of light, okay, in opposite directions. Okay. The question is, what is the relative velocity of one with respect to the other? What is the relative velocity of A with respect to B, and what is the relative velocity of B with respect to A? Yeah, this is very common. So, I mean, we all have traveled in trains. So, you see, when you travel in a train in a certain direction, so if you can always feel that the train which is moving in the other direction to you is somehow moving. What's the relative velocity of that train? It moves quite fast, isn't it? Okay. And in this, so we're going to find out a similar situation here. Okay. So, here how do you do that? So, we take particle B to be at rest in frame S prime. So, which is moving with S with the other frame S with an uniform velocity c by 2 here. So, again the velocity of A relative to S is what is measured in S is c by 2. Okay. So, what is the relative velocity? So, what you are going to find is the velocity of A relative to S is c by 2, and therefore, relative to S prime, and you see S prime is the frame in which B is taken to be at rest. So, that is the frame if you find this velocity, of A with respect to S prime, you are going to find the relative velocity with B. That is it. So, you use the velocity addition formula here, so that you are using the primed coordinates here. So, u prime is u minus v, 1 minus u v by c square, and then you just put in the numbers c by 2, the perfect the proper numbers here, and what you get? You get 4c by 5, still less than c. I mean, if it had been the Galilean way, it would be c, but here it's 4 by c. And what's the other way around? The velocity of B relative to A, it should be exactly the opposite, right? So, it's minus 4c by 5. You could have also used the velocity addition formula to get this speed. I mean, that you can do it as an exercise, of course. Okay, right. So, having now seen how velocities are done, let us go to some of the other corollaries of special relativity, and especially an interesting thing called length contraction. Okay. So, what is it? So, it just tells you that the length of a moving body appears to be shortened in the direction of its motion. Okay. So, if moving bodies appear to be shorter, okay, we are going to find out how. Okay. So, for this, let us consider a rod. Okay. The end points of this rod are in S prime, let us say. So, this rod is in S prime and it is at rest on this x axis. Okay. So, just consider an unidirectional thing here, a one dimension thing here, and you have you have the ends of this rod as x1 prime and the other end as x2 prime. Okay. So, the length of the rod which is at rest in this frame is, you call that at L0. This is, you just measure this. How do you do? So, it is not you just measure, you can take a measuring tape, put it on one end of this rod and just put the other one at the other end and they measure it, that is all. Okay. So, so how do you, what do you find that? L0 is x1 x2 prime minus x1 prime. Okay. However, one thing is to be noted here is that we are not bothered about the time at which these two measurements are done, because this thing is at rest. So, it does not, we are not bothered about the time. Okay. So, you that is what you do, you leisurely put one end of your measuring tape on at x1 and then go and put the other end at x2 and then see that the length, that is all. Okay. Now, what happens? I mean, if you want to measure this in some other frame S, let us say. So, you want to measure the length of this rod S. Now, remember, relative to S prime is moving with a certain velocity, and hence the rod which is at rest in S prime is also moving with a certain velocity with respect to S prime. Okay. So, that is it. So, in this frame S, right, remember that the rod is now moving parallel to the x prime axis with a certain uniform velocity v. Okay. Now, it is very important that to measure the length of the rod in the S frame, its n coordinates must be measured at the same instant of time. Okay. This is very important now. Okay. Now, for this what you need, of course, you need synchronized clocks, and then when you have two different observers who are going to measure the end points of the rod here. Okay. So, let us say at this particular time t is equal to t0 in S prime in S frame, that is, not in the S prime frame. The two ends are measured as x1 and x2. Okay. So, what is the length of this rod in S frame? You are going to just subtract these two coordinates. So, L is equal to x2 minus x1 and say okay. So, this is my length in the S frame, okay, and relative to which the rod is moving with a certain velocity. But remember, there is a relation between the quantities in the S frame and the prime frame. In the frame in the x prime coordinates and the unprimed coordinates x which are unprimed. So, they are given by the Lorentz transformations. Okay. So, we use the Lorentz transformations. So, what is it again, just to remind you. So, what is x prime? So, that is x minus v t. Now, here at a certain, so on the right hand side of this equations, your all these quantities are in the quantities measured in the S frame. Okay. So, and the left hand side, it's the quantities which are measured in the primed frame. Okay. So, from this, so you can find the relations of x1 prime and x2 prime in terms of the corresponding quantities in the S frame. Okay. But remember, along with these positions, the time also enters into this picture. But then the point is that the time you measure this at the same time, you have measured the ends of the rod in S frame at the same time. So, it is going to be the same here. So, if you subtract these two equations, what do you get? So, you get x2 prime minus x1 prime, that is equal to x1 x2 minus x1. Okay. And what does this give you? What is x2 prime minus x1 prime? That is L0. Okay. So, that is the length of this rod in the prime frame, and then what is x2 minus x1? That is L, that is the length of the rod in the S frame. So, and then notice that the denominator is still there. Okay. So, that is root over of 1 minus v square by c square. So, you get this expression. So, what is the length of this rod in the S frame? Remember, it is moving in the S frame, it is as if the rod is moving with a certain velocity v. Okay. You see that it is L is nothing but L0 into root over of 1 minus v square by c square. Clearly, you see that this L, the length as measured in the frame in which the rod is moving, is less than L0. Okay. Well, to be very exact, it should be less than equal to L0. You can even have v is equal to 0 in some sense. Okay. So, if v is equal to 0, L is equal to L0. Okay. So, this shows that the length of the rod, it appears to be shortened in a frame relative to which the rod is moving. Okay. So, this is length contraction. Okay. Okay, but having said that, let us just be familiarized with another concept of the thing called proper length. Well, you just seen that if you know, if this rod is moving with a certain velocity, if it moves at different velocities, okay, it's going to be the measured length is going to be different. So, if a rod has a length L in a frame relative to which it is moving uniformly with a velocity v1 along its length, this is important, it is moving along its length, because there could be a case where it is not moving along its length, it is making some angle with the x axis. We'll try to see if we can do that too. And similarly, let us say in another frame, this rod is moving with a certain velocity v2, and then the measured length is L2, then you must have figured out by now that L1 divided by root over of 1 minus v1 squared by c squared is equal to L2 divided by root over of 1 minus v square v2 square by c square is equal to L0. Okay. And what is L0? Well, you can also write L0 in the form of the other things that you have written on the left. L0 is L0 by root over of 1 minus 0 square by c square. So, it is as if moving in a frame which is which is at in which the rod is at rest. Okay. But what do you see? you see that the quantity L by root over of 1 minus v square is invariant. It is not changing. You changing. So, if you change v, the length changes, but then the whole quantity of the length divided by root over of 1 minus velocity square by the speed of light square, that is becoming invariant in all inertial frames. Okay. And this is called the proper length. Okay. So, the proper length of a rod is of an object is a length measured in a frame in which it is at rest. And obviously figured out that this is also the largest of all possible length measurements of this rod. Okay. Having done this theory, I think it might be useful if we have a few examples. Okay. So, let us again have an observer A, and let this person find the length of a rod to be 1 meter, and then and also to be moving with velocity, let us say 0.8 c. Okay. Now, this same rod, if it appears to have a velocity 0.6, the speed of light, okay, relative to another observer in another frame. Okay. So, see that we have not specified the length here of this rod. So, the first question that we ask ourselves is what is the proper length of the rod, okay? And secondly, what will be the length measured by the second observer, okay, relative to which it is moving with velocity 0.6 c, not 0.c, I am sorry. So, what is the proper length? We just saw in our previous slide that it is the length divided by the root over of 1 minus the velocity square by the speed of light square. Now, you do that, you do the length of the rod was 1 meter. So, you have put 1 meter there, and then for the velocity was 0.8 c, so which was like 0.64 c square, take the square of that is, and then you see that this proper length is L0, and L0 is 1.67 meters. Okay. So, this is the length that would be measured in a frame, in the rest frame of the rod. Okay. So, what would be the length then measured by the other observer relative to which it is moving with a certain velocity? Okay, that is simple. The if you call that as L subscript b, LB, that is L0, 0 in the sense that that is the proper length, L0 into root over of 1 minus v square by c square, and then the v here is 0.6, okay, 0.6 c, that is. So, you find here it is 1.33 meters, that is all. So, when it was moving with 0.8 c, the length was 1.8, the length was 1 meters. When it was when it is moving with a lesser speed of 0.6 c, the length measured appears to be 1.33 meters. Okay, and then so you see the higher the speed, the shorter is the length that you want to measure. Okay. Right. So, we come over to another interesting case. Now, in the previous cases, we had this rod to be parallel to the x axis. Okay. But now we are having this rod, let us say it's moving, making a certain angle with the x axis. Okay. So, it is not moving along its length. So, there is a component along its length, along the x axis, and then there is a component along the y axis also. Okay. So, the y axis and also I mean the z axis is also there, it is protruding out of the screen. Again, I have not drawn it so that the figure does not look too clumsy. Okay. Now, what we take this rod in the x y plane itself, okay, and then this rod, it's in the S prime frame where is at rest, and then it's making a certain angle theta 0, and then this S prime frame is moving with a uniform speed v with respect to the S frame. So, the question that we ask ourselves is that, so what is the length of the rod as measured in the S frame, okay, and what angle does this rod make with the x axis in the S frame. Okay. So, if it is with a certain angle theta 0, is it theta 0 again in the S frame? Well, we were to find out. Okay. So, remember of course that this S is moving with a certain velocity v relative to the common x prime x axis here. I mean S prime is moving with a uniform velocity v. Okay. So, what do we do in the S prime frame? Measure what is the length of the rod along the x axis. It is x2 prime minus x1 prime, and you are going to find this out to be L0 cos of theta 0. Okay. And then if L0 is the proper length of the rod, that is, and what will be the component perpendicular to this direction of motion. So, it is y2 prime minus y1 prime, that is simply L0 sine of theta 0. Okay. Now, when measured in the S frame, okay, now remember in the S frame this rod is moving with a certain velocity, with a certain uniform velocity v with respect to the S frame. Now, so the n coordinates of this rod at time, you are measuring this n coordinates of this rod at a certain time t is equal to t0 here. So, you find them to be x1 y1 and x2 y2. So, what is this difference x2 minus x1 here? Well, it is L cos theta. Okay. So, L is the length as measured in the what that with the length of the rod in the S frame, and then the theta angle is the angle that will make with the x axis in the S frame. Okay. Well, so x2 minus x1, that will give you what the along the length along the x axis, that is L cos theta, and then y2 minus y1, that will be L sine of theta. Okay. So, how are they related? Well, you have just figured out again that it is well by the Lorentz transformations, of course. So, you use the transformations equations between the prime coordinates and the unprime coordinates, and you find them to be, well, what it is given on your screen. So, the things it is done at the prime coordinates on the left hand side and the unprime coordinates on the right hand side. Okay. And then the unprime coordinate, that is in the S frame, the measurement of the length is done at a certain instant. Okay. So, you definitely require 2 observers with synchronized clocks to do this, and then synchronized, so then measurement is done exactly at t equal to t0 here. And since it's the rod is moving parallel to the x prime axis here, y coordinates are the same. Yeah. So, y1 prime is equal to y1 prime is actually equal to y1, and y2 prime is also equal to y2. Okay. So, now if you subtract x2 prime from x1 prime and y2 prime you subtract from y1 prime, or the other way around. So, what do you get? You get this, you get x2 prime minus x1 prime, that gives you x2 minus x1 divided by root over of 1 minus v square by c square. Okay. And y2 prime minus y1 prime is y2 minus y1. So, therefore, you get L cos theta, which you know to be L0 cos theta 0, which you know to be the length along the x prime axis, that is x 2 prime minus x 1 prime, is again equal to L cos theta divided by root over of 1 minus v square by c square. It is very interesting, of course. And then the in the direction perpendicular to the direction of motion, that is in the y direction, L 0 sin theta 0 is same as L sin theta 0. Okay, so what is the length of this rod in S frame? Okay, so we come back to our old question, and what angle does it make with the x axis in the S frame? Okay. So, to do that, all we have to do is divide those angles which we found, and we found that we will find that its tan theta 0 is equal to tan theta root over of 1 minus v square by c square. How do you do that? That is simple. You have this relations L 0 cos theta 0 is L cos theta divided by root over of 1 minus v square by c square, and then this L 0 sin theta 0 is L sin theta. So, we divide the equation with the sine with this equation with the cos, and then you get this tan, that is all. So, this gives you first the angle, so the angle is not the same, the angle with which the angle this rod makes with the x axis in the S frame, okay, is theta, and then the angle this rod makes with the S prime with the x prime axis in the S prime frame, that is theta 0. Okay. Okay, so just check that they are not the same, and then this is the relation you can use to find these angles. What about the length? Remember, L was the length in the S frame. So, L square, this very simple identity of L cos theta squared plus L sin theta squared, and we know these what is L cos theta and L sin theta in terms of the proper lengths in the S prime coordinates in the coordinates of the S prime frame. So, we get the everything in terms of the proper length, in terms of all the quantities in the primed frame. Okay. So, interestingly, this L, that is the length of the rod, comes out to be L, right. So, L, so what is it? So, in the S frame, it's moving with a certain velocity, uniform velocity v. So, that is and the length is measured to be L, and that L is equal to L 0, that is the proper length of this rod, the root over of 1 minus v square by c square, and now see that you have a cos square theta 0. Okay. So, what is theta 0? That is the angle the rod makes with the x prime axis. That is the frame in which it is at rest. Okay. Okay. So, let us spend a couple of minutes with this equation just to see whether it is right or not, and whether remember when we were doing some length contraction formulae earlier, it was L is equal to L 0 into root over of 1 minus v square by c square, and then the rod was moving along its length. So, if we put theta 0 is equal to 0, so that simulates this the system or the rod to move along its length, we get back our old length contraction formula. Okay. L is equal to L 0 into root over 1 minus v square by c square. Okay. But what happens if you put theta 0 is equal to pi by 2, okay, that is perpendicular to its direction? Well, L is equal to L 0 then. Okay. So, if it is moving perpendicular to its direction, so the perpendicular component that is not contracted. So, let us be more specific. So, the component of the length parallel to the direction of motion is length contracted by a certain amount dependent on the velocity, okay, and that quantity is root over of 1 minus v square by c square, and the component perpendicular to direction of motion is unaltered. Okay. Right. So, that being our idea of length contraction, uh, in the next segment, in the next lecture, we are going to talk of another consequence of special relativity, and that is called time dilatation. Till then, goodbye.